Ladies and gentlemen, thank you for being here. So my name is Roscher. I work at Eckhardt, and today I will talk about A20X, which is a high-strength aluminium alloy for additive manufacturing. So to give you a very short background on myself, so I joined Eckhardt in January this year. Before joining, I completed a PhD at the Max Planck Institute for Ion Research in Düsseldorf. And the topic was development of high-strength aluminium alloys for laser powder bed fusion. And I worked in the group of Professor Erik Jägel, who now works here and is head of the organizing committee of this conference. So I'm definitely happy to be here. And I will start this presentation showing two very quick slides, okay, introducing the company I work at, after which we will get into more detail on A20X. So what does Eckhardt have to do with additive manufacturing? Eckhardt produces metal powders, okay? So I've listed some of the markets or applications Eckhardt produces products for. Now, while it may not seem like it on first sight, the common theme among these applications is metal powders. They are often used for optical effects. So to give you an example, if you see a silver car on the street, there's a very good chance that the metallic pigments that are used to make the coating or the car painting look silver are produced by us. Now, apart from the optical business, we also produce powders for functional applications or technical applications such as corrosion protection and additive manufacturing, and we will get into more detail here. So the headquarters are based in a very small village in Bavaria, in Hartenstein. This is also where my office is. And we have quite a few production sites and sales locations around the world, but two interesting ones are this one in Wackersdorf. This is where we produce about 10,000 tons of aluminium powder per year by gas atomization. And more importantly, maybe in this context, is Eckhardt TLS in Bitterfeld, formerly TLS Technik, which is where we produce only spherical metal powders specifically for AM. And these are the types of alloys that we produce. Our specialty is titanium, copper, aluminium-based alloys, even though we can atomize pretty much anything, as long as it's not radioactive or highly toxic, and as long as it's conductive, which is very much related to the atomization techniques that we employ, because next to standard crucible-based atomization, we also use a crucible-free process, which is electrode induction melting, inert gas atomization, which is good, good if you want to atomize high melting materials or highly reactive materials such as titanium. And one of the alloys that we atomize using electrode induction melting is A20X, okay? So the chemical composition of A20X is shown in this table. It's essentially a aluminium, copper, magnesium, silver alloy with additions of titanium and boron, which are present as titanium diboride, ceramic particles. So A20X is patented and was in the past supplied by a company called Aluminium Materials Technology, AMT in the UK. This company was acquired by Eckhardt, including the patent, so now this product is supplied by Eckhardt. So what A20X really stands for is aluminium alloy A205, okay? And indeed, A20X was started out as a cast alloy, okay? And this is quite some time ago, but back then A20X quickly found industrial applications in the aerospace industry in the form of investment and sand cast components. So the casting part of the business is still ongoing, but what I found interesting is that the problem that A20X solved back then was very similar to the problems that we are tackling now, which is the formation of major metallurgical defects during the process. We have seen it a few times, so the main one being solidification cracks or hot cracks, and A20X solved that by grain refinement. As it turns out, this alloy is also very well, if not better, suited for additive manufacturing. So one of the key features that enables the good processability is the high degree of grain refinement that is achieved during solidification. This is related to the titanium diboride addition and ultimately results in the suppression of cracks. So in this particular example, the average grain size is about 1.5 microns in the as-built A20X sample. During heat treatment, which is typically employed in actual applications, the average grain size slightly increases but stays within the single micron region. What also helps with regards to processability is the fact that A20X does not contain volatile elements such as zinc or magnesium in high concentrations. So the process window is relatively large, a few hundred millimeter per second scanning speed, relatively constant, high relative densities and low surface roughness. So processability is good, but what about tensile strength? So this is room temperature tensile strength, tensile testing results for as-built and heat-treated specimens. Now, what should be noted is that this is not peak strength, okay? So T7 heat treatment refers to solution heat treatment followed by over-aging, so artificial aging beyond peak strength. And this really is a common procedure for 7000 series alloys, for instance, which are often employed in the overaged state with the goal of balancing tensile strength, fatigue strength, toughness, and resistance against stress corrosion cracking, as opposed to just maximizing yield strength. So shown on the right is the effect of testing temperature on UTS and yield strength. So at 200 degrees C, the yield strength is still above 300 megapascal, okay? And to put this into perspective, so these are typical competitors, so if we're looking at aerospace materials, this is what we're looking at, the benchmarks. And so ROD 7075 as well as 2618, which is a high temperature aluminium copper alloy. And A20X compares very favorably to these alloys, which is a huge, so taken together with the good ductility, this is a huge advantage as it opens up applications at 150 degrees C or higher where many other aluminium alloys cannot operate. So the question that follows is, why does this aluminium copper alloy have much better high temperature properties than other conventional high strength materials? And there's two factors. The first one is related to the presence of titanium diboride particles. Now, as we can see in these micrographs, the titanium diboride particles are relatively homogeneously distributed in the as-built material. And these particles, of course, represent obstacles to dislocation motion, and more importantly, they do not coarsen during temperature exposure. And maybe a short anecdote that I can tell. So we had a project related to Formula 1 motor racing, and there we had to modify the material. So we had to bring down the titanium diboride content to comply with the regulations. Okay, so from 4 to 5 rate%, which is the usual range, to 2 rate% titanium diboride. And I can say so much that reducing titanium diboride while keeping everything else constant decreases temperature stability with regards to strength, okay? So titanium diboride definitely plays a role. However, there's a second factor, and this is related to the types of nanoprecipitates that form during heat treatment. So as we can see in this TM micrograph, there's quite a high volume fraction of plate-like nanoprecipitates present after heat treatment. We can identify two phases actually. One is theta prime, which is what you would find if you aged binary aluminium copper as well. It is simply part of this precipitation sequence when aging supersaturated copper-containing alpha solid solutions. There's a second phase, however, this is omega phase. In this phase you only get in aluminium copper alloys that contain magnesium, some magnesium, not too much. And this phase is especially promoted in alloys containing magnesium and silver. Okay? And this phase, omega phase, is the most potent strengthening phase in 2000 series alloys that do not contain lithium. Okay? With lithium you can get even higher strength. But moreover, it is also considered to be the phase with the highest thermal stability among the types of nanoprecipitates we can choose from in 2000 series alloys when designing microstructure. So this contributes to the good high temperature properties. And all of these comments were on strength. Now, especially in aerospace industry, of course, many catastrophic failures have occurred due to cyclic loading, fatigue failures rather than simply overstressing a component. Okay, so fatigue performance is critical and a requirement if we want to exchange conventionally produced components with LPBF produced components. So in this figure I have included two types of A20X fatigue data points. Dark blue is standard room temperature fatigue testing. So LPBF processed, heat treated, machined. The points in blue and in bright blue were generated by taking those test bars and aging them for 1000 hours at 230 degrees Celsius and then testing them at 230 degrees Celsius, okay? Which is a very extreme example showing that at least some fatigue strength is still preserved under such severe conditions. Now what I have included here is very simple data on wrought aluminium alloy 7050, and what we see is A20X has fatigue performance that is comparable to conventional high-strength material alloy, high-strength aluminium alloys, which makes it suitable for aerospace applications. Now, on the note of severe testing conditions, many aluminium copper alloys are prone to stress corrosion cracking, which is a form of corrosion that is made significantly worse when stressing the component. So standard stress corrosion cracking tests involve keeping the test piece in a stress condition up to 80% of the yield stress in a salt mist chamber, 3% sodium chloride mist chamber for prolonged periods of time. And what we see is that A20X samples pass standard stress corrosion cracking tests for 30 days without failure. And all of these tests, we do not carry them out ourselves. This is all done by certified laboratories, so that people believe the values. This is one option. The other option is that these tests are carried out by project partners directly, who need to carry out these tests as part of internal qualification processes. Because indeed, A20X is in aerospace serial production. So really LPBF serial production of flying parts. Okay, and the powder. So for the castings, this has been going on quite a bit longer, but the powder now also got its own aerospace material specification, which makes it by now a proven solution. Okay, for aerospace applications. Okay. So here I will end the presentation. Okay. Thank you very much for listening, and if you have any questions, feel free to ask or reach out to me afterwards. Always happy to discuss. Thank you very much.